Hello everyone, I am Said Ali Ajwad and I will be presenting our paper entitled Leader Following Consensus of Second Order Multi-Agent Systems with Switching Topology and Partial Aperiodic Sample Data. Here's the outline of the presentation. I will give you a brief introduction and then we'll be discussing problem statement and main results along with some simulations. Multi-agent system is a group of multiple autonomous agents which can interact with each other to accomplish some common objective and reach to some common goal. The study of multi-agent system is inspired by nature, where we can find various examples of natural species which work in cooperative manners, such as bird flocking, mammal herd, ants formation, and bacteria swarming. Inspired by these natural phenomena, engineers and researchers have produced various applications of multi-agent system. For example, distributed computing is an example of a multi-agent system where multiple computers are used for the computation purpose, and it will reduce the computation power on each computation efforts on each computer, and this distributed computing can be used to for larger computation. Similarly, we have satellites information which we use to cover the maximum area of Earth for communication. Robotics or multi-robot systems is one of an important example of mass application where multiple robots are deployed to achieve some goals which cannot be accomplished by a solo robot. Sensor network is another example of application of mass. So to control the behavior of a multi-agent system, there are basically two strategies. The first one is known as centralized control scheme, in which there is a central unit which is responsible of controlling all the agents. It receives information from the agents and then it computes the corresponding control input and then send it back to the relative agent. There are some serious issues associated with the centralized control scheme, since the central unit is responsible for all computation. So in the case if the central unit is failed, then whole system will be destroyed. And if we increase the number of agents, then the computation load on the central unit will also increase. On the other hand, we have distributed control scheme where agents communicate with their neighbors and compute their own control input based on the information they receive from their neighbors. So there is no central unit involved in it, and the computation is divided among the agents. So even if one of the agent is failed, even then this whole system won't be destroyed. It will the other agent will keep doing the task. So therefore, the distributed control has various advantages, like it is more efficient, robust, and scalable. Consensus is one of the major problems in mass. Consensus means that agents are agree and reach to some common state. So starting from their initial conditions, they reach to a common state known as consensus state, and this is known as consensus seeking or leaderless consensus. Sometimes these agents are not only have to reach to a common state, but they are also required to follow some reference trajectory. So this reference trajectory can be produced by a leader. That is why it is known as leader following consensus or consensus tracking. The leader could either be real or virtual. So now come to problem statement. Let's consider that we have a multi-agent system with n followers and a leader. The dynamics of the follower is of second order, where xi is the state vector, which includes both position ri and velocity vi. Ui is the control input which we have designed to achieve leader following consensus. The dynamics of leader is also of second order. So mathematically, leader following consensus means that the norm of the error between the agent I state and the leader state approaches to zero as time goes to infinity. In this paper, we consider various practical communication constraints. For example, the first constraint is that each agent can only measure and transmit its position information, which means that it is equipped with only position sensors. It does not have any velocity sensor or acceleration sensors, etc. This is a very practical assumption since sometimes to reduce the cost of an agent, uh, the, we can actually equip it with some less sensors, and moreover, transmitting partial information will also reduce the communication bandwidth, which will eventually reduce the cost of communication. Secondly, the sampling instance at which the data is being transmitted is irregular and asynchronous. In fact, in practical scenarios, it is not possible to have some uniform sampling rate. And second, and asynchronous means that the sampling rate of agent I does not depend on any other agent in the network. So they are totally independent. The only consideration on the sampling rate is that it is between some maximum and minimum value. Moreover, we consider the directed communication topology only, which means that if agent 2 can receive information from agent 1, it doesn't mean that agent 1 can receive information from agent 2. In various practical applications, the communication link between the agents does not remain constant. For example, sometimes the distance between two neighbors is increased so much that there is no more communication possible between those agents. So in that scenario, they have to switch to the other neighbors, or sometimes even the link fails due to any other reason. So the switching topology is a very practical assumption. So we have a finite possible communication graph set, which is G, and the graph is switching dictated by a switching function sigma. So though the graphs are switching among each other, but the switching shouldn't be very fast, because fast switching could lead to chattering or Zeno effects. So which means that there should be some dwell time, which leads us to a very important definition of average dwell time, which says that for a switching function sigma and the time period between t1 and t2, there exists n sigma, which describes the number of switching between that time interval. So if n sigma is less than some constant plus t2 minus t1 over tau a, then tau a is called average dwell time. We also assume that each possible communication graph contains a directed spanning tree. Come to the main results. So the idea is to use a trivial continuous time leader following consensus controller. But since we have only discrete position data, so first we will use continuous discrete time observer to reconstruct both position and velocity in the continuous time, and then these estimations can be used to design the controller. So here is our controller, where C bar is the coupling strength, lambda is the controller gain, and we can see that we are only using position and velocity, which are estimated through an observer given by 4, where theta is the tuning gain of the observer. Uh, in controller equation, Aij is equal to 1 if agent j can receive information from agent I, and 0 otherwise. Since the communication link is not constant, so Aij is also a function of switching function sigma. So the theorem says that if we have a second order multi-agent system with our design controller and observer, and if the tuning parameters follow the condition 5 and 6, and the average dwell time satisfy the condition 7, then we will have leader following exponential consensus. These conditions are achieved through Lyapunov stability analysis, so these conditions are only sufficient. However, these conditions give us some very good insight of tuning the gains of both controller and observer. For example, we can see from inequality 5 that the observer gain theta is inversely proportional to maximum sampling time tau m. So if the maximum sampling time is high, then we have to choose theta uh, low accordingly. And 6 shows that lambda should be less than theta, uh, which means that we have to have our controller dynamics slower than the observer dynamics. So for simulation purpose, let's consider we have three graphs, G1, G2, and G3, and the graphs are switching according to some switching functions given in this figure, which have minimum dwell time of 1 second. The tuning gains are chosen as theta is equal to 12 and lambda is equal to 0.8, and the sampling is between 10 millisecond and 150 millisecond. So in the first case, the leader is stationary at position 2, and all the agents starting from their initial condition reach to the position of the leader, and similarly we have velocity consensus as well. Here is an example of a sampling instance at which the data is transmitted from one agent to other agent, and we can see it is totally non-uniform. In the second case, the leader is moving with the velocity of 2 meters per second, and we can see that both position and velocity consensus has been achieved. So let me conclude this presentation. We have discussed the problem of leader following consensus of multi-agent system with switching topology, and the mass is considered to subject to various communication constraints like unavailability of velocity and input states, and so moreover the sampling period is irregular and non-uniform. In this paper we consider that each possible communication graph has a direct spanning tree, but in future we can work on a case where the communication graph does not have a spanning tree, but only joint or the union of graphs have spanning tree. Thank you very much.